Hello, everybody. Welcome to the downstream processing and bioseparation process. We will continue the lecture on extraction. Right. Previously, we talked about the principle of extraction and also like the effect of PS to the extraction process. For this case, in this lecture, we will focus on the extraction with the batch process and continuous process. The sample or example are the simple technique for the operate like the batch extraction, as I show you in the first figure. This is the simple technique. This is separated by the separate funnel. After you mix between the solvent and solute or like aqueous solution, with the organic solvent, until we wait until the separate by phase separation, heavy phase in the lower phase, light phase in the top phase, and then you can separate the funnel. It's easier for the batch process for this case. And for another system, right, we have like the mixer and setter. Have a mixer and setter. The mixer we use like to mixing between like the aqueous phase, and we add like the organic solvent, like mix together, and also we have some dispersion like liquid phase in the dispersion, and then we send the mixer to the setter. The setter is used to phase change between the heavy phase and light phase. The heavy phase should be water system, and the vinyl acetate is the light phase for this case. For this case, we use the vinyl acetate, acetic acid, and the another solvent to separate aside from the water. And also for this case, we have some the mixer in this case, and the overflow is sent to the like phase separator, like the heavy phase at the bottom and light phase at the top also for this case. And is the another device. That's another device. For this case, for most cases, these three cases we call like the mixer setter extraction. Mixer setter extraction. And the most important equipment that can be helped to improve the separation or the contact between two solvent to system. We call this is the impeller, something like this. The first one we call it is the Magnetite impeller. The second one is the centrifugal turbine, twist bed turbine. This is the pro impeller. This is the centrifugal turbine. And this is the twist bed turbine. And also this is a flat bed turbine. For this case, it is the flat bed like paddle. This is the function for this is due to improve the mixing and due to improve the contact between solute and solvent, That is the difference we call the configuration of the impeller. That will help increase the contact between solvent, solute, solvent, something like that. Okay. If we first consider the technique to analyze for this system, the first step we can consider the analytical method. For this case, we consider the equilibrium constraint for dilute system. For this bioprocess, mostly the product is in the water is very, very low concentration that we can consider a dilute solution. Okay. For the equilibrium concentration relationship, we can require the equation like equation 17, like X equal to Ky. K is partition coefficient. For this K is the equilibrium constant, not partition coefficient. And X is the product concentration or solute concentration in extraction solvent in light phase. K is the product concentration or solute concentration in the heavy phase of its solvent. K is equilibrium constant. This is the equilibrium relationship X equal to Ky. In this case, it's the linear relationship. It's possible to nonlinear also for that. Okay. In the next relationship that we would like to consider, we call it the mass balance. The mass balance. If with this system we have like the initial step and final step for batch operation. if we consider batch operation, if we consider its initial step and final step, we can solve at this out, in and out like this, or if we consider like the continuous process, and also we will flow in, flow out continuously. We can consider flow in, flow out continuously, or continuous process. That's right. Okay, for this case, we can draw the flow chart, right? Okay, this is the feed. S is the heavy fat, flow rate or amount of heavy fat. Y is amount of solute in heavy fat or desired product in heavy fat. And output, we call it the raffinate fat. The raffinate fat is the heavy fat in the output. And the heavy fat in the S is the amount of flow rate. That's right. Y is the fraction of solute in the heavy fat, in the raffinate fat. That's right. Mostly we can consider S is constant during process because it's dilute solution. We can approximate it's constant. And so when that we add to separate the solute, as we got L. XF is the fraction or concentration of solute in the solvent. And L is it quite constant due to the pure solvent or into the dilute solution. X also X is the solute concentration or fraction of solute in the light phase, or we call it the active phase. Please remember that the output of the heavy phase we call it raffinate phase. The output of the light phase we call it active phase. Our product, yes, our products in this phase. That's why this is our product. Okay. And for this case, we assume no solute in the solvent. No solute in the solvent, that means XF equal to 0. That's right. S and L are approximately constant. If you make the mass balance, that's right. If you make the mass balance, that means solute feed into the extraction equal to solute out of the extraction. Because it's flow in, flow out, it's continuously, we have no accumulation term. And for this case, there is no reaction term. The generation and consumption is 0. If we recall like the general material balance, that's like input, in, side, plus out, T, that's right, minus, this minus term, that's right, input minus output plus generation, that's right, minus consumption, and equal to accumulation term, that's right. For this case, for there is no reaction, no generation, no consumption, no accumulation, because flow in, flow out, continuously, that you get input equal to output for that case. How about input for this system? Input for this system is we balance on solute as it amount of less of feed system. That's right. You multiply by YF. YF is the solute concentration of solute fraction. Is the amount of solute divided by the amount of feed. This is the solute input. And also L multiplied by XF. That's right. XF equal to 0 for this case. There is no solute in the solvent. That's right. Output is SY and L. SY and L. As you get, this is the mass balance. And then you can rewrite this equation. You get X equal to KYF divided by 1 plus E. Y equal to YF divided by 1 plus E. That's clear. What's about E? E is the KL divided by S. Aside from this, E equal to KL divided by S. And also we can calculate the fraction of extract of P. P is the fraction of extract. P is equal to LX divided by SYF. SYF is amount of solute in the feed. That's right. LX is amount of solute in the extract feed or the light feed. And equal to E divided by 1 plus E. That's right. You can use this to estimate like the extract or the product that we can separate or we can recover. Okay. Previously, we talked about the analytical method. You can solve for X, you can solve for Y, and then you can calculate like the fraction of active. And then we can utilize the graphical method. The graphical method, we use the relationship between equilibrium and mass balance to construct the graphical method. Okay. For this case, you plot the mole fraction in phase Y and mole fraction in attack. We plot Y and X. For the equilibrium line, equilibrium line, we know like X is a function of y, like equal to ky, something like this. You plot this step. And also you plot the mass balance. For mass balance, you get like this equation. From this equation, you can rewrite, and then you obtain with equation 40. We have these two equations. You can plot equilibrium line and mass balance line. This is equilibrium line, X and Y. And also you plot X and Y for the operating line. Operating line. And finally, we can calculate the attract field. X and Y after you attraction. This is the composition of X. This is the composition of Y after you attract. X is the composition of solute in the definite phase. Y is the solute in the attract phase. This is the composition after you separate by the graphical method. Okay. For this example, this is a bacterial attraction. Bacterial attraction. Water containing 6.8 milligram per liter of asteroid is attracted with initially pure methylene dichloride. For this system, we have aqueous solution of steroid. That means steroid dissolved in water. We use methylene dichloride and the organic solvent to remove the steroid from water. That's that. For this case, the equilibrium constant is 170. That means K. That's that. This is K. The ratio of water to solvent is 82. Water to solvent is 82. That means S over L is 82. Okay, the question is, what is the concentration inorganic after the attraction? The concentration inorganic after the attraction will mean by the concentration of X. That's right. Okay. If this case from the given value, we can calculate E. E is KL divided by S. From the problem, you know S over L equal to 82. K is 170. You get E equal to 2.07. And then from equation 19, you can calculate X. You can calculate X. X is the amount of the solute in the organic, in the attract field. Okay, X equal to KYF divided by 1 plus E. You know E, you know K. And 1 by F, the initial concentration of steroid in the aqueous phase. And then you can calculate amount of steroid in the organic or in the attract phase. That is 377 milligram per liter. Milligram per liter. And what fraction of steroid has been removed? For this case, we calculate the fraction of steroid or the percent of steroid that can be removed from the aqueous phase. We can calculate by P value. P equal to E divided by 1 plus E. You know E already. And then you can calculate P equal to 0.7 approximately or 0.67. That means about 67% of steroid that can be removed from the aqueous system. And another example, we try to stripping the amino acid. For this case, it's the liver process. The liver process. For a non-essential amino acid, the equilibrium relationship between toluene and pure water is equal to 0.001 mole per liter. Why? For this case, we plan to contact 4.7 liters of toluene containing 0.006 molar amino acid with 1 liter of water. what fraction of amino acid can be extracted. For this case, we use the water to recover amino acid from taurine. That's right, from taurine. Okay, for this case, the equilibrium is not in the form of equation 7, but it is liver. That's right. We cannot usually analyze it in equation. That's right. Okay, we can pause mass balance or the opening line with like this from the previously we know like x equal to h divided by l y plus y. But for this case we can write y equal to l over s. That's right. X minus x. That's it. Y overhead is 7.7. That's right. For this case, overhead and y is 0.006. For this case is xf. That's right. For this case is xf. This case is L over S. That's right. L over S is 4.7 liters of taurine. For this case, taurine is live and S is heavy phase water. That's right. But for this case, it's liver operation. Liver operation, you can rearrange this is y as a function of x. That's right. Y as a function of x, we get y equal to L over S xf minus x like this. Okay. Y equal to L over S. L over S is the taurine divided by water. It's 4.7. 4.7. F is it 0.006 is the amount of amino acid in taurine in the life in the beginning. Yes. Minus x. Okay. And the intersection we plot between like operating line. Previously we plot x and y. For this case we plot y and x. Yes. Is it the equilibrium line is the nonlinear equation because is it x squared equal to 0.01 y. This is the equilibrium line because y was x. And this is the operating line. That's right, because y was x. And then you get the intercept for operating line and equilibrium line. And then you can find x and y. X is approximately 0.0035 and is 0.012 mole per liter. Y. Y is it the concentration of amino acid that remove from taurine to water. And the fraction of extract P is then calculated. Previously, the P is expressed in terms of LX divided by SY, but for this case, it reverse. It reverse. We separate from the life to the heavy fat. It should be SYF. Right. It should be SY divided by LX. It should be SY divided by LX. SY is the amount of amino acid go to the water. Divided the amount of amino acid in the initial taurine. We get 0.43. That means about 43% of amino acid can be removed by water. Can be removed by water. Okay. And the next, previously we talked about the batch process or continuous process. And the next thing is the stack extraction. Mostly previously, if we use only one stack, we get about 43%. 40% and about 57% is stay in taurine. If you would like to get this pure, you get the higher concentration of solute, or we would like to increase the efficiency to remove of solute, you can use more than one step. This is the example of the master step operation. The master step operation. Like this, we feed. This is the feed that we would like to separate the beer. We separate the penicillin in the beer. The mixture. Liquid solution. We feed in this direction. This is the extractor and setter. For this case, we feed mix together with the extract right? This. Okay. This is the solvent feed. This is the mixture feed. solute or penicillin that's mixed in the water or in beer, right? This is the feed. This is the pure solvent feed in this direction. This is the counter current technique. Okay. For this case, the feed is mixed with the solvent. This solvent is out of the second step, and then mix together. And then the penicillin move to the amino state. And then we feed out more penicillin in the amino state. For this case, the feed amino state mix to the raffinate phase. To the raffinate phase from the first system. The raffinate phase or the heavy phase, that there are some amount of penicillin in this. We would like to remove more penicillin. We use it to contact with the solvent. With the solvent. For this case, the solvent come from the first step. Okay. This is the solvent amino state. This is the feed. We contact more than one time. For this case, about 3 times. The step feed in step 3 contact with the solvent from step 2. Right? After extraction, the extraction phase is out of the step. It is our product. And the raffinate phase also contact again with the solvent, this, and extract again. That's right. And also more amount of solute go with the extract phase or solvent, and then like this again and again, something like this. And also for the first step, solvent from the first step after extraction, mix to raffinate like this. This is the counter current operation. Right. We can display this in terms of the box flow diagram. This is the feed. This is the raffinate feed. This is the feed solvent. This is the extract feed. That's right. Extract feed. We represent by stack 1, 2, n-1, and n feed at n+1. That's the output of the heavy feed is -1, S1. And feed of pure solvent is L or X0. That's right. R as L or Xn. For example, feed to state N is Syn+1, R as Syn. The light phase feed at Lx minus n-1 or Lxn, like for example. Feed to the first state is Sy2, R as Sy1. Feed solvent is Lx0, R as Lx1, for example. For this case, we need also write the equilibrium relationship and the mass balance also. The equilibrium relationship is the amount of solute in the light phase is a function of equilibrium constant multiplied by the amount of solute in the heavy phase. That's right. For example, Xn and Yn. These two terms is in equilibrium. That's like the output of solute in heavy phase, the output of solute in the light phase is in equilibrium for this assumption in equilibrium with the K value. And also, if we balance for the first step, if you balance for the first step, for this case, there is no generation, no consumption, and no accumulation because we operate steady state or in 4 out continuously. For this case, for input Sy2 plus Lx0 equal to Lx1 plus Sy1. That's like this for balance for the first step. That's like balance for the first step. And then also you can substitute x1 by equal to ky1, something like this. And then you can solve for y2 equal to e plus 1 y1. That's right. And then you substitute e like this. And also if you balance for the second step, for the second step, Syt plus Lx1 equal to Sy2 plus Lx2. That's right. For this case, and also you can relate for this x2 equal to ky2, something like this, and then you can solve for y3. That's right. So for y3 equal to this equation, and then you can more make the mass balance step 3, step 4, and step n, something like this. And finally, we will get like yn+1. Yn+1 is the feed to the step n. That's right. Feed to the state n. Feed to the state n. That's right. And then you can get yn plus 1 equal to e power n plus 1 minus 1 divided by e minus 1 and multiplied by 1. Determinant e is the KL divided by k multiplied by amount of light fat divided by amount of heavy fat. It should be amount of fluid. It should be amount of fluid. And finally, you get this relationship between the amount of solute in heavy fat, as I have said, and stage 1. Stage 1. Okay. How about the fraction of extract? Fraction of extract, amount of percent of solute that can be extracted from the aqueous phase. That means P equal to amount of extract phase that's out of our system. Amount of extract phase divided amount of feed of solute. That's right. This is amount of feed SY, amount of extract plus FY, and amount of extract is L. This amount of extract. This is amount of feed. That's right. It's maybe amount of feed or folded of feed. That's right. Y is amount of solute divided by the amount of feed. And first you get this term is amount of feed. Okay. Okay. This is P. P is amount of solute in the extract phase divided amount of solute in the feed. This is the amount fraction of product or fraction of extract that we can recover from the feed. If you multiply by 100, you get percent recovery. And then you can rearrange this. That's right. You can substitute xn, you can substitute yn plus 1, you get p equal to 1 minus yn divided by yn plus 1. Or you can display in this term. That's right. Display in this term. For that case, if E becomes very large, P approach 0. That means you can separate all amount of the solute from the aqueous phase. That's right. If E equal to 1, P is maybe n divided by n plus 1. That's right. If E approach 0, P approach 0. That's right. It's low value or low efficiency to remove. That's right. Okay. For that case, we can use this as the graphical method also. When you utilize the analytical method. For the graphical method, we need two systems. Also, right, we need the equilibrium relationship. That's right. It means that's right, concentration of solute in the light phase. And also from the mass balance, you can express X is a function of Y. That's right. X is a function of Y. X is X divided by Y plus 1 Y1. Xn is the amount or concentration of solute in the extract phase. Yn plus 1 is the amount of solute in the feed. Y1 is the amount of solute in the heavy phase in the output. That's right, in the output. And then for this case, you can contract the graph by plus X and Y. That's right. X is the amount of solute in the light phase, Y amount of solute in the heavy phase. And the first one, you can construct the equilibrium line like this. It's maybe linear or non-linear. It depends on the information. This is the equilibrium line. And this is the operating line. Operating line comes from this. And the first one, you have to contract the feed. The feed condition. Mostly we feed X, Y1, X0. That's right. X0 and Y1. You know the feed. That's right. You contract the feed point first. Okay, at this moment, the feed. How about the feed? If you back to our flow chart, the feed at yn plus 1. That's right. For Y1, this is the output. Okay, we know output and we know X1. We know X0 and we know Y1. For this case, we can correlate the output and output at this state. So you contract the output of state 1. You contract the output of state 1. Okay, it's the equilibrium. That's right, equilibrium. That's Y1. x0. You get this. This is y4 interface of this is y4 feed. Okay. This is the y1 is the output, the sum of soyuz in heavy phase at the output. This is amount of soyuz in heavy phase in the feed. That's right, in the feed. This is the output. For this case, at the output, equilibrium with x0. x0 is 0 for this case. x0 is amount of soyuz in the solvent is 0. This is 0. And then you can calculate y1, x1 like this. You contract the triangle, right? x1. That's right. You draw this to x2, y2, xt, yt, and x4, y4, like this. And then you can calculate the number of steps. Is 1, 2, 3. Let's add the 3 steps. And sometimes you can write, if you know y5, that's right. y5, you can contract like this. Okay, this equilibrium line. It's approximately like is 1, 2, 3, about 4.7 or 4.8. If you would like to get to 5, it's maybe like this. But this is about 4.5, 4.5 steps, but you can round up to 5 steps. That's it, 5 steps for this case. Okay. For example, right, you would like to antinomycin, the attraction from the qualified fermentation beer. Fermentation beer that is contained 260 milligram list of the antibiotic. It to be attracted by butyroacetates there. For this case, the aqueous phase, we call beer, which contains 260 milligram of antibiotic. For this case, we use butyroacetate to separate the antibiotic from the aqueous solution. S is heavy phase, L is light phase. Because the beer pH is 3.5, the equilibrium constant for this case is 57. We plan to raise S equal to 450 liters per hour, L equal to 33 liters per hour. And we would like to recover 99% of antibiotic in the feed. 99% of antibiotic from the feed is removed to the live phase. That's me. Okay. For this case, calculate the state. How many steps will you need to complete 99% of recovery? For this case, you can write the y as a function of e, like this equation. That's right. And also, you know e, it is KL over S. You know L, you know S, you know K, it's 4.69. And then you can use this equation like this. And also, you know, right, the equilibrium composition is for x is 0.01. You use this like to calculate 0.01 yn plus 1. That's right. Okay, so this is the equation from, you can use this equation. That's right. Yn plus 1 equal to this term multiplied by y1. Y1 is y1. Y1 is the soyuz concentration in the output. Soyuz concentration in the output. For this case, the soyuz concentration in the output or soyuz concentration in the heavy phase is only 1% of the feed. Because 99% is removed to the butyl state or again. That means only 1% of the feed. 1% equal to 1% of y1 plus 1, because y1 plus 1 is so you in the feed. That means so in the feed is 1% is 0.01. Okay, and then you can calculate this term. That's right. Is y x plus 1 is 100. Sorry, is yn plus 1. You can rearrange this term. That's right. You can cancel this term. Cancel this term. That means you can calculate, and then you can estimate n. For this is about 2.8. For this case, you can estimate is by this technique. Okay. right? And also we use like the same problem, but we need to calculate by graphical method. By graphical method. For this case, the equilibrium relationship with xn is equal to 57yn. 57yn. Because the k value is 57. For this case. And also we can determine the operating line. The operating line we use is relationship. We need two equations, equilibrium line, you know already, and operating line. The equilibrium line xn is ky. This is xn. Xn is the amount of solute in the extract field. Yn plus one amount of solute in the feed, one amount of solute in the heavy feed in the output or refined feed. That's mean you know right? Xn equal to 57yn and xn equal to this is S over L. That's right. S over L y n plus 1 minus y1. Okay. This is S over L equal to 12.2 yn plus 1 minus this is the y1 multiplied by 12.2. You get this term, right? You get these two equations. And then you put x and y like this. X and y like this. You know x1 and x0 equal to 0. You know y1 like this. Y1. And then you can draw the triangle, right? One is approximate 2, right? It's y2 and x2. This is x2, it's y3, y4. It's approximate 1, 2, 3, 3 state. That's right. It's the same. The same period it is about 2 point. Sorry. It's about 2.8. It's the same answer. That's about 2.8 for the graphical method. It's approximately 3. That's right. It's the same. And another example, right? The butyl acetate extract in the previous problem contained 3.1 gram per liter of antibiotic and is produced at 37 liters per hour. We plan to with the extraction with water. For this case, after you extract by butyl acetate, the amount of the antibiotic is 3.13 gram per liter of the solution. And for this case, we would like to remove this by water. That's right. We plan to what did extract with water at pH 6 or with K equal to 0.11. We will use the same 3-stage extractor as before, but will be certified with 95% recovery. The question is what water flow it should be used. For this case, it's reverse operation. That's right, with reverse operation. And then after, if you would like to check this, you can do by yourself. Okay, this case we will express in terms of x. That's right, in terms of x, but previously we expressed in terms of y. That's right, because our is y is heavy fat. That's right. But for this case, our heavy fat in terms of x. Right. Because the butyrate is the heavy fat for this case. This heavy fat is x. But light fat is water. For this case. The equation is liquid. You can show by this, which is the equation for this case. Okay. And also, where the action factor is still equal to KL divided by S in the case. That's right. This is x. That's right. And then you know n is 4, and this is x1. X1 is 95% recovery. 95% recovery, that means the amount of antibiotic remain in the nutrient set is 5%. It means 0.05 multiplied by the feed. For this case, you can evaluate E equal to 0.44. You know E, you can calculate S. That's right. S is the amount of water. E equal to KL divided by S. You know E, you know L. That's right. You know K, and then you can solve for it. It's about 9.2 liters per hour. Okay, for the Last example for this lecture, we will talk about the glucose isomolecule equation. For this, we would like to extract the protein, the protein by organic solvent, but mostly the result is not good. But if you use like pure organic solvent, we can separate pure protein. For that case, we use like the aqueous two-phase system. We use the aqueous two-phase system using the immeasurable aqueous solution of polyethylene glycol. We use the aqueous polyethylene glycol as aqueous system or the second system. That's right. For this case, we utilize the polyethylene glycol 1550 at the light fate. That's right. And aqueous potassium phosphate is the heavy fate. That's right. Aqueous potassium phosphate. The distribution coefficient K equal to X over Y for enzyme glucose isomerase is 3. And the enzyme is feed in the heavy fate phosphate. That's why we call the aqueous phosphate. And also glycol. Okay. We have a 4-stage extractor which we hope to separate this enzyme. If we set the flow rate S over L equal to 2, what percent of enzyme can be recovered in the life phase? Okay, for this case, if we're entering the concentration by Wi-Fi, then the fraction P is Lx4 divided by S Wi-Fi, and this expressed in this equation. And back to our equation. If we have 1, 2, 3, 4, the field should be Wi-Fi. The output is Y1, input is X0, and output is X4, something like this. And the equation for E, that's right, E in this, that's right, E4, this is E5, something like this. That's right. And then for the value of E equal to Lk divided by S equal to 3 over 2, and then you substitute E. In this case, you can calculate P is about 0.686. That means 86% that we can recover. We can recover protein by using the two-phase aqueous solution, like in the term of polyethylene glycol and aqueous potassium phosphate for this case. I will stop like the lecture for this, and we'll continue for the next lecture of the differential extraction. That's the differential extraction.